In the next several videos, we are going to study trees in some detail. So a tree is a special kind of graph that appears quite frequently in many applications in computer science and mathematics. A tree is a connected graph which contains no cycles. So there's two pieces here. We need our graph to be connected and we need to contain no cycles. So here's an example of a tree. If we look at this tree, we say, this graph is connected. Every node is reachable from every other node. And also, remember the definition of a cycle. A cycle is a path that begins and ends at the same node. You can think of it as a circle that doesn't backtrack. So here we can see, for example, that if I start here at this node in the middle, there's no way for me to go on a loop and get back to that node. If I go out here, for example, I can get back here on a walk, but for a path, I would be stuck because paths are not allowed to repeat any nodes other than the beginning and the ending node. So once I walk from here to here to here, there's no loop that will bring me back here. I have to retrace my steps. So this tree has this property. It's connected and it is not. It contains no cycles. On the other hand, here's a different graph. So this graph does contain cycles. So in this case, if I start at this node here, let's give that node a label, we'll call it U. If I start at node U, then I can go on a little loop here, 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 that brings me back to U. So that would be a path. This path does not repeat any nodes other than U itself. And it brings me back to where I started, so that's a cycle. So this graph contains cycles. It is not a tree. Disconnected graphs also cannot be trees. So these are there are two bad cases. Big picture, when you think of a tree, you want to visualize something like this. It's a connected graph that does not have any cycles in it. This one has cycles, no good. There's a few other pieces of terminology that go along with trees. So one way we often draw trees draws on the idea of a root. So a rooted tree is just a regular tree, but we include some specific node that we call the root, and that node is special. So here's a tree again. This tree has been drawn in such a way that there's a node that's clearly on top. This node is special. This node is our root node. Right there. The root is really nothing more than a tool for drawing when we're drawing graphs and can be very useful when we're talking about graph algorithms. We'll see an example of that in a later video. But fundamentally, the root is nothing more than simply a choice of a single node in the tree that we're going to call special. Finally, there's one other piece of useful terminology in trees that I want to highlight. So you'll notice that in the tree that I've drawn here, there's several nodes, for example, this one, that have degree 1. There's only one edge going into that node. When I have a node with only one edge going into it, a node with degree 1, we call that a leaf. So this tree has several leaves. This is a leaf right here, as is this one and this one. On the other hand, a node like this one is not a leaf because that has degree 2. So now that we have some definitions and concepts in place, let's go further and explore some of the structural properties of trees. There is another property of trees that actually does what we call characterizes the trees. So a characterization is something that uniquely specifies the set of all trees. We can think of it as an alternative definition or an equivalent definition. So here's the equivalent definition. So our previous definition was connected and no cycles. This time, theorem, a graph is a tree if and only if for any pair of nodes, u and v, there exists exactly one path from U to V, no more and no less. So if we look at a picture of a tree here, let's label this node can be my U and this node can be my V. Now, in this graph, there is exactly one path from U to V. And it goes along this edge, then down here, and then over here. And there are no other paths from U to V. Any other way you could try to navigate from U to V would involve backtracking and going over the same node twice. Now, on the other hand, suppose that we added an edge to this graph. So suppose that we add this edge, this graph. So now visually, no longer a tree, it contains a cycle. And indeed, now we have the old path from U to V, but we also have this new path where I can follow this sequence of edges, in addition to the old one, which I'll mark in a different color. So because there are two distinct paths from U to V in this graph with the added edge, that's a sign that this is not a tree, and indeed you can tell because we also have the cycle here. So our theorem says that this is a characterizing property of trees. If you have a graph where there's exactly one path from U to V for every possible choice of U and V, then you are looking at a tree. So from a proof writing perspective, the thing to notice here is that we're looking at an if and only if statement. So that means we need to prove two directions. So we need to prove that being connected and having no cycles implies having a unique path between every pair of nodes, and we need to prove that having a unique path between every pair of nodes implies that you are connected and have no cycles. So let's go ahead and get started on this. I need to prove both of these two directions, so I'm going to start by proving the rightward direction. So in the rightward direction, I am going to assume that my graph is connected and contains no cycles. So I'm going to make that assumption, and then what I want to do is I want to prove that every pair of nodes in this graph has a unique path. So then, for any pair of nodes in the node set, okay, so I need to show exactly one path. So that's the same as saying no less than one and no more than one. Okay, so if I pick these two, then there must be at least one path between them by the hypothesis that we are connected, and at most one, because two distinct paths would create a cycle. Now, this is a little bit tricky, the idea that two distinct paths would create a cycle, and it's actually something that we can prove separately. It's a little bit nicer to kind of look at it as a picture, though. So if we look at the picture here with the two distinct paths that we drew, so we have the blue path and the green path. So the blue path and the green path together are not a cycle, because a cycle is a path and they have some repeated edges here if I tried to do one after the other. However, we can see that there is a node somewhere on both of these paths with the property that if I focus on that node, so this guy right here, if I look at just the blue and the green paths from U and then up to that node, indeed, I have constructed a cycle. So this is kind of a proof by picture, and indeed it's possible to write a more algebraic proof of this as well, that if I have two paths from U to V, then somewhere in those two paths together, if I add edges together, I must be able to produce a cycle in my graph. Okay, so let's say that that is going to work for us for now, and go ahead and do the other direction of the proof. So in this direction, I'm going to assume the unique path property. So the unique path property is that between every pair of nodes, there is exactly one path. So we need to prove both connected and no cycles. So first of all, to prove connected, we know that G is connected because what connected means is just that there's a path between every pair of nodes. There is a path between any pair U and V in the node set. A tree guarantees that, or the unique path property guarantees that there is exactly one path between U and V. One is all I need in order to infer that G is connected. Now let's do the second part. We also need to show no cycles. Furthermore, G has no cycles since if U and V are on a cycle, then there are two paths between them. So what does this mean? Suppose that we had a cycle. Then if I pick two nodes on this cycle, like here U and W, I can get to between U and W along two distinct paths. I can go this way, or I can go that way and then that way. That violates the unique path property, which I assumed, and therefore there must not be any cycles. Since I have no cycles and I am connected, I am looking at a tree. So this proof shows us that I can define a tree in one of two equivalent ways. One appropriate definition is that a tree is a graph that is connected and contains no cycles. A second appropriate definition is that a tree has the unique path property. For every pair of nodes, there is precisely one path between them. And I can use either of these definitions when I am reasoning about the structure of trees.